Hey everyone. Last time I left off with this theorem right here, so this was 1510. And sorry, I was a little rushed at the end. Right, I had office hours coming up right then, so I had to kind of finish quickly. So let me just remind you. So it goes like this: if we have a couple of normal subgroups of G, then so let's say period. So then G is equal to H cross N if and only if every element of G can be uniquely expressed as something in the form little h times little n, where little h is in capital H and n is in capital N. Right? So the idea of internal direct product corresponds with a unique expression, a unique decomposition as h times n, or little h times little n. Now, let me do one quick example. So in R, or actually I want to work in R star, right? So in the group, the multiplicative group of non-zero real numbers, consider the subgroups R plus, right? That's right, all positive all positive integers, and I also want to consider the subgroup -1 and +1, right? So we can easily check that that's a subgroup also. So note that if x is in R star, well, it's either positive or negative, right? Right, so then x is equal to either x times 1 in the case that x is greater than 0, or x is equal to minus x times y minus 1 in the case that x is negative, where, right, if x is negative, then minus x lives in R plus, and if x is positive, then x lives in R plus. Right, so what that tells us is that we can express any non-zero real number as something, and this is unique, as something from R plus and something from plus or minus 1. Right, so so we can say it like this. So R star is equal to R plus times, and this looks a little bit weird, let me put a little dot there, times -1 +1, right? Every element can be written, right, as something from R plus times something here. And now the uniqueness comes from the fact that if we look at the intersection, R plus intersect -1 and +1, right, the only thing we get is the identity, right? So the intersection is trivial, and so what does that tell us? So conclusion, R star is equal to R plus times cross -1 +1. In other words, R star is the internal direct product of these two subgroups right here. And of course, by the way, both of those, since R star is abelian, both of those subgroups are normal. Here's a definition. A group G is indecomposable if, whenever you express it as an internal direct product, you essentially did it trivially, where meaning that one of the groups is all of G and the other group is the identity. So how do I want to phrase that? If whenever G is equal to H cross N, either H is trivial or N is trivial. Right, so what that means is that you can't, an indecomposable group is one for which you can't write it as an interesting internal direct product. One or the other of the groups is the identity. And notice, if one of them is the identity, then the other one is all of G, right? So if I have H equal to E, that means N equals G. And if N equals the identity, then H has to equal all of G. So for example, Z is indecomposable. And the reason, now think about who the subgroups of Z are. They are multiples of one given number. So if Z equals AZ, I'll write this. Oh yeah. Now let's say this quickly. So if A and B are integers, then A times B is an element of A times Z intersect B times Z. In other words, anytime you take two subgroups, you are not going to get them to have intersection just equal to the identity, right? 0 in that case, right? The number AB will always be in the intersection. Oh, and I guess I should have said here, to make this useful, so if A, B are greater than or equal to 2. Right? So as a kind of final discussion on this idea of internal direct product, what I want to do, and I kind of alluded to it yesterday, we use the term direct product in two different settings, as an external direct product and an internal direct product. So suppose G is equal to H cross N, and let H bar and N bar, capital H bar and capital N bar, be any groups where H is isomorphic to H bar and N is isomorphic to N bar. So just take an isomorphic copy of H and an isomorphic copy of N. So what we have here, G, when I write equals here, what we're saying is that G is this internal direct product. And then suppose that we have a couple of groups, H bar and N bar, that match H and N. So if alpha is the isomorphism from, which way do I want to go? From H to H bar, and beta is going to be an isomorphism from N to N bar. So if these are isomorphisms, then let's define an isomorphism, and I guess I'll call this one phi, from G to H bar cross N bar. Phi. All right, so now we know that G is the internal direct product, and so every element can be expressed uniquely as something from H times something from N. So all elements are of this form, little h times little n. And the obvious thing to do here is to write this as alpha of H comma beta of N. because of the uniqueness, this function is well defined. All right, so uniqueness of expressions, all right, essentially theorem 15.10, guarantees, so uniqueness expressions guarantees, you should check this, of course, guarantees that, actually there's really nothing to check, right? Uniqueness gives us the guarantees that phi is well defined. And I'm just going to say check that phi is an isomorphism. It's not difficult to do, but you should check the details there. And so what does that tell us then? It tells us that G, so conclusion, G is isomorphic to H bar cross N bar, where here this one is the external direct product, where this one in the beginning was internal. So where do these words internal and external come from? Internal means inside, right? And so this group is the internal direct product of its subgroups. The subgroups lie inside. And so when you're an internal direct product, you can be expressed in terms of something from H, capital H, times something from N. When you're an external direct product, you can be expressed as an ordered pair. Something from H bar, comma, something from N bar. So in the end, right, there's this correspondence. And what's this correspondence look like? Well, the correspondence between the internal and external direct product is essentially going from multiplicative notation to ordered pair notation, right? It's just a renaming, essentially, or renotating. I don't even know if that's a word, but a renotating? Yeah, renotating. Right? Going from multiplication to ordered pair, right? And that's it. So that's why we use the same term. They are essentially the same concept algebraically because of this isomorphism right here that connects multiplication to writing things as ordered pairs. Okay, so I mean, you know, I guess that's the that's where I want to leave you when it comes to direct products. And then there's one more topic that I want to cover. I mean, this is our last lecture, so this will be the last of the new material. All right, but I do want to discuss one more new thing here. So well, let's let G be a group. And let's choose a couple of elements. So let's say, and let G and H be elements of G. The commutator, so this is a commutator of G and H is the element, well, it's this thing right here, so it's GH, G inverse times H inverse. So that product right there is called the commutator of G and H. It's sometimes denoted with brackets G comma H. So when you see this in algebra books, bracket G comma H, it means that thing right there. I'm not going to worry about that. And one thing to notice, so let's say note that G and H commute if and only if their commutator, so G H, G inverse, H inverse, equals the identity, right? So the commutator, that word comes from this fact, right? That the commutator is trivial if and only if, or it's equivalent to saying that G and H commute. Now, let's let S equal the set of all possible commutators that we can form in G. So that'll be the set of all GH, G inverse, H inverse, where we let little g and little h run through all G. So form all possible commutators. The commutator subgroup of G is, and it's typically denoted G prime, and it is the subgroup generated by capital S, right? So it's the subgroup generated by all commutators. Sometimes, so G prime is also denoted and I'm not going to use this notation either, but sometimes instead of writing G prime, they'll write in brackets G comma G. So let's see now, what will a typical element in G prime look like? Well, it'll look like all possible, it'll look like a product of commutators, right? So a typical element in G prime something like this. So it would be something like a G1, H1, G1 inverse, H1 inverse times G2, H2, G2 inverse, H2 inverse, dot, 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 sorry, I ran out of room, Gn, Hn, Gn inverse, Hn inverse. That would be right up there, right? So it's a product of commutators. That's what somebody in G prime is going to look like. Now, here's the key observation. If, who do I want here? So if we take a commutator, so if X equals GH, G inverse, H inverse, and A is anybody in G, then A, well, I'm going to have to write it over here, then AX A inverse, right, this is A times GH G inverse H inverse times A inverse. That's equal to, and now I got to be careful here, well, yeah, let me just write it down. It's equal to A G times H, AG inverse times H inverse times HA H inverse A inverse. Ah, and guess where that lives? It lives in G prime. So a conjugate of a commutator is a product of commutators. Consequence, and I'll just leave this as an exercise. So as a consequence, G prime, so you can use this fact right here, G prime is a normal subgroup of G. Right? The commutator is always a normal subgroup of G, and that's interesting for this reason. Now we can form the quotient. Right? And this quotient has a name, so the quotient G mod G prime is called let's put it down here, the abelianization of G. And here's the reason. So what we're essentially doing is we're forcing things that may not have previously commuted as cosets they're going to commute. So, so the reason for this name, if x and y are in G, then x G prime, y G prime, x G prime inverse times y G prime inverse, that's equal to x, y, x inverse, y inverse times G prime. And this lives inside G prime, so this is equal to G prime. So what we just showed then is that the commutator of the corresponding cosets is trivial. Thus, x G prime, y G prime is equal to y G prime, x G prime. Right? So what that means then is that this quotient is abelian. Now, so let me just do an example or two. Of the abelianization. So our first example, let's look at the abelianization of let's do S sub n. And I want to do this in steps. So the first thing, let's look at the product. So AB times CD. So I want to look at the product of these two transpositions, right? So AB is some element of Sn, CD is some element of Sn. They're both two cycles. And this is equal to, well, I'm going to write it as, it's a little lengthy here, but it's going to be AB times AC times AB times AC times BC BD BC times BD. So you can just check, right, that this is equal to this. And notice, what is each one of these? These are each commutators. Right? So as a consequence, AN is contained in Sn prime. Right? What do we have here? This even permutation, right? What I have is the product of two cycles, right? Two transpositions. So this is even. Can be expressed as a commutator, which means that it lives inside Sn prime. And since every even permutation is going to be a product of things like this, right? Every time you have a double, it can be written as a commutator, right? That shows us that every even permutation can be expressed as a product of commutators. So this, I guess, would be the second step. So here, so like this. So step 2, commutators are even, and so Sn prime is contained in An. So what do we have then? The commutator subgroup of Sn is equal to An. So Sn mod Sn prime is equal to Sn mod An. Because An as index 2, this is a group of order 2, which means it's isomorphic to Z2. Right. Now, so let's see, and let me just, what do I want to do? Do I want to do this example? How are we doing on time? Oh, I guess we're still good. All right, so, yeah, let's do one more example. And then I want to talk about why one would actually care about this abelianization. So let's do the abelianization of An. So first recall, if n is not equal to 4, then An is simple, which means that, what does that mean? If n, yeah, if it's not equal to 4. Well, that means that it has no non-trivial proper normal subgroups. Right? So since An prime has to be, it's always, right, the commutator subgroup is always a normal subgroup. Right? So here we see that An prime has to equal the trivial subgroup, or An prime has to equal all of An. All right, those are our only two options because it's got to be a normal subgroup, which means it either has to be trivial or it has to be everybody. But remember, the commutator subgroup is definitely not trivial, right? Right, so since, right, I mean, just compute it. It's got a whole bunch of things. Or here's another way to say it. An is not abelian already. So since An prime is non-trivial, we conclude that An prime has to equal all of An. Therefore, the abelianization is trivial. So we're missing one example, or this is true for n not equal to 4. So now we need to consider the case where n is equal to 4. So now for n equal to 4, let's say recall that A4 has no subgroup of order 6. And so, so what? A4 prime has to have order, so it's got to be one of these divisors. And so who's it going to be? It's going to be the order of A4 would 1, 2, 3, or 4. So V consist of the following. So it'll have the identity. It'll have 1, 2 times 3, 4. 1, 3 times 2, 4. And, sorry, I ran out of room again. 1, 4 times 2, 3. This is isomorphic to the Klein 4 group. And you can check, so let's say check, that V is a normal subgroup of A4. Now since what? Well, okay. Where'd it go? Since the index of V in A4 is equal to 3, A4 mod V is isomorphic to Z3, right? There's only one group of order 3. And so I'm going to say, and so V has to contain, yeah, oops, I just wrote that right. Yeah, has to contain, so A4 prime has to be contained in V. And here's the reason. A4 prime is the smallest normal subgroup of A4 that makes the quotient abelian. Right? So in general, the commutator is the smallest normal subgroup for which the quotient becomes abelian. So anytime, if we get a quotient that gives us abelian, the denominator has to contain the commutator. Yeah, so let me say this. Because, so the reason that I can say this right here is because A4 prime is the smallest normal subgroup of A4 for which, or which yields, let's say, an abelian quotient. So now, note that each of the elements in here are actually commutators. So note that, or let me say check. That the reverse containment is also true. So check that V is contained in A4 prime. And the way you would do that is show that each one of these elements, right, can be expressed as a product of commutators. So conclusion. A4 prime is equal to V, and so the abelianization of A4, so A4 mod A4 prime is isomorphic to Z3. Okay, so there's an example, and now I just want to talk briefly about why the abelianization is important. And we'll do this as a theorem. So theorem 15.11, if G is isomorphic to H, then G mod G prime is isomorphic to H mod H prime. Isomorphic groups have isomorphic abylianizations. Fine. The way you usually use this theorem, and this is one of the sources of algebraic topology, by the way, for those of you who are interested or going on to algebra or to learn about topology. This theorem is typically used in the contrapositive form. And let me explain first why that would be. So if two groups are isomorphic, great, find the isomorphism and verify that. Showing that two groups are not isomorphic can be extremely difficult. But we have fundamental theorem that tells us all about abelian groups. So as long as we're dealing with finitely generated things, you can, in a finite amount of time, decide whether two abelian groups are isomorphic or not. Right? It's an actual doable problem. And so, if you can then show that the abylianizations are different, that allows you to conclude that the groups are not isomorphic. Right? So if their abylianizations are non-isomorphic, we get to conclude that the groups are non-isomorphic. And so that gives us a way to show that certain groups are not isomorphic. So let me just kind of sketch the proof here. And this proof, it's a nice application of the first isomorphism theorem. You should practice this one. So let's see, what do we have? So let's let alpha from G to H be an isomorphism. And then define, let's say phi from G to H mod H prime by phi of little g equals the obvious thing. It will be alpha of G times H. And I'm just going to say check that phi is an epimorphism with kernel of phi equal to exactly G prime. Now apply first isomorphism theorem. So this theorem, even though it's the proof is really easy and it maybe doesn't look that exciting, this is kind of a big deal, right? It is very difficult in general to show that groups are non-isomorphic. One way to do so is to compute their abylianizations, and if you have non-isomorphic abylianizations, then you can conclude that G is isomorphic to that G is not isomorphic to H. Now, there are certainly situations where the abylianizations are isomorphic, in which case you can't make any conclusion about whether these two groups are isomorphic or not. All right, so this is it for new material. So you essentially have survived all of my lectures for this class, Math 481. So on both Monday and Tuesday, we're going to basically do review. I'll come up with some sort of review session for both Monday and Tuesday. So that'll be done live. And then the final exam is, depending on which your section, I think one of them's, and don't quote me on this, I think one of them's on Monday and one of them's on Friday. I'll post this and you should be able to look it up also. But I think one section, the exam's on Monday, the other one's Friday. And all right, so we'll see you then. I don't even know what that means. We'll see you either on, we'll see you Monday and Tuesday, and then I'll talk about the exam at that time. Okay, see ya.